Hello, hello. Hello, 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 hello. So, hello everyone, welcome to today's class. I hope I am audible and the slides are also visible. So, let's start with today's session. So, we are covering this heat अभी मत तो बात में देना, मीटिंग चल रही है. Sorry for that. So, we are covering this subject of heat transfer, whereby we are discussing your doubts related to the course contents discussed in the previous weeks. So, in the earlier week, in the week 1 we covered the introduction to the course, motivation behind the course. Then we started with the conduction, energy balance, 1D steady state concept conduction, where we introduced this resistance concept in order to simplify the heat networks or the system whereby we have composite heat transfer rates or composite materials. Then we covered this resistance in a composite wall case. So this was all we had covered. Applications. So these were the few basic laws that helped us to solve the numericals. So the first one was the Fourier's law of heat conduction, then Newton's law of cooling. That is, heat flux is proportional to the thermal conductivity and the temperature gradient in case of conduction. Whereas in case of convection, the heat flux is proportional to the heat transfer coefficient and the temperature difference between the surface and the ambient temperature. So this is convection. Then the last one is the radiation. So yes, then we studied this combined case of conduction and convection that occurs mostly in practical scenarios. Then we covered this resistance concept, and then we solved few of the questions related to week 1, and then in the last week we had covered this resistance in the radial systems, then heat generation in plane and cylindrical wall, again heat generation, and we introduced these extended surfaces, those were fins, and then different formulation of fins and fins of cross-sectional area. Since that was all. So this was how we derived the temperature across fin or the heat transfer rate when we have this extended surface or fin. So basically we solve this basic second order differential equation corresponding to different boundary conditions. So, and according to the boundary conditions that we have used, we get different kind of solutions. So one thing to note was that the area over here, the cross-sectional area over here was constant. That is, for over here you can see that it will be rectangle of same area throughout the fin. Similarly over here it will be a circle of a same area throughout the fin. In today's class we will be covering the scenarios where the area is varying. For example, in this case only, if I had this such kind of tapered fin. Sorry for that. So if the fin was like this, so this is my entire area of the fin. So over here you can see that the cross-sectional area will change as we increase the length. So for that we just need to, for example, let's consider the perimeter of this surface over here is P, and the thickness, let's just consider the elemental thickness as dt. So the area, heat transfer area, will become A times of P dt. That is basically P into dx. So this P into dx we will replace over here, and then we will solve the second order differential equation. That won't be very straightforward to solve, so you just need to look into the notes and you will get certain formulas that you can use to find the heat transfer rate or the temperature distribution across the fin. So this was the temperature distribution as well as heat transfer rate for the systems where we had constant cross-sectional or constant heat transfer area, you can see, corresponding to different boundary conditions. Then we define these two performance metrics. One is the fin effectiveness, that is the ratio of actual heat transfer with fin upon the heat transfer without fin. And then the other one was efficiency, that is the actual heat transfer upon the maximum possible heat transfer that would have occurred if the fin was at the base temperature. So yes, that was all from last class. So if you have any doubt related to the week 1, week 2, you can ask right now, or else we can start the content of today's week in 5 minutes. Okay, so let's start with the content of week 3. So as discussed earlier, so we are covering this, we had covered in the course this extended surface with the varying cross-section area, and the basic philosophy I already discussed with you. Also we will be covering the scenarios where we have multiple fins. So until now what we had covered was only a single fin with varying cross-sectional areas, such as this rectangular fin or cylindrical fin, and then there was also this pin kind of fins. But what happens in most of the practical scenarios, what will happen is not a single fin but a multiple combination of such fins are available. For example, in this application, you can see that these are all the fins. So this is one fin, two fin. So we have this multiple fins, and that are used to facilitate a faster heat transfer for faster cooling. So yes, we will be covering that multiple fins today. Then until now we had only covered the terms where we had this temperature gradient in one direction, that is only del T by del X. We had not covered the variation along Y or along Z direction. So for example, we defined this Q of X is equal to Ka del T by del X, and this basically comes by this term plus Q dot is equal to 0. So this we wrote it as del 2T upon del X2 is equal to 0 if this is the 0. So now we will be covering whereby we have this 2D plane wall. So for example, along with X direction, we will be also having the variation in Y direction. So we can just consider a rectangular plane, 2D plane, X and Y. Then we will be covering this transient analysis. So all those until this 12th lecture we discussed the scenarios whereby we had this steady state, that is the time, that is the all the parameters were not changing with respect to time, the temperature was constant with time. But in this transient analysis we will study whereby the temperature will change with time. So for example, if you remember in this heat balance equation, you would have taken the left hand side, that is I think dt by dt alpha upon rho Cp, I think some constant over here, let's say beta. So this term dt by dt was taken as 0, but now we won't be considering it as 0, we will be considering in order to find the variation of temperature with respect to time, we won't be neglecting this term. So for that we will be covering this lumped capacitance method, whereby we assume that the entire object or entire solid will be at a uniform temperature and its property will be uniform throughout the space, that is there won't be any spatial variation. Then we will be covering this full method, whereby we will be considering spatial variation, and then this semi-infinite case where we can see the whereby one of the axis or one of the direction is infinitely long and we have this variation in one direction only. So yes, that is all the contents of today's class. So few of the definitions that will be helpful to solve the questions that I will be discussing in a couple of minutes. So we will be discussing that. So the first one is the overall surface efficiency, that is for the cases whereby we have this multiple fins. So let's say if this is my base or wall and I'm having multiple walls over here. So multiple fins also, this is one fin. Similarly, I'm having second fin over here, and likely I'm having n fins over here. So how to define the overall efficiency of this field or the overall surface efficiency? So we define it by using this n naught. So n naught was already defined as qt, that is heat transfer rate, upon maximum possible heat transfer rate. Maximum possible heat transfer rate we defined as h. A was the area through which convection occurs, and the temperature difference. Then correspondingly we can also define this resistance over here by this equation, that is 1 upon overall surface efficiency upon h into at. Now in case of multiple fins we need to find this total area. So total area will be nothing but the area of the individual fins, that is if there are n fins and each area of each fin is af, then we can write it as n times af, and the remaining area of base. So all these areas will be AB. So from the overall area of the base plate we have to subtract the area of these fins. So that thing you need to keep in mind while calculating this AB. Then the total heat transfer rate by convection from the fins and prime, that is the unfinned part, that is basically this part, and the base part is expressed as this term. Now in this equation we can replace all those values, such as the value of AB we can replace, and we will be getting this equation. So ultimately the overall efficiency or the overall surface efficiency can be written in terms of the number of fins, the area of each fin, total fins, and NF. So NF is the efficiency of individual fins. So for particular fins we have this efficiency NF, so that we have to use over here. So and yes, so yes, those were the two main formulas that we will be using. This is the 1 and 2. So this essentially means that if I am having two fins of efficiency NF and area of heat transfer rate AF, so I can replace them in the resistance diagram as a parallel combination of two individual resistances. Okay, so So this is for the multiple fins AF, and this second resistance corresponds to the heat transfer through this base. Okay, so the overall, we can write it in terms of overall surface efficiency eta naught HAF, where eta naught is given by this equation, and if we have to find the overall heat transfer rate, then we have to use this equation. Then we will move on to the 2D systems, or in general any n-dimensional conduction analysis. So why do we need to solve in 2 dimensions? So the main objective is to obtain the temperature profiles as well as obtain the heat flux across this 2D system. That is basically useful in design to obtain the maximum and minimum temperature possible and the total heat transfer rate. So this is the Laplace of this temperature. That temperature will give this 3-dimensional equations. But now we are only considering 2 dimensions, so we can just neglect this, and we have to solve this 2-dimensional second order partial differential equation in 2 variables in order to find the temperature profile varying across x and y. So how do we go along with that? So just to give a brief overview, so for example, we are having a rectangular plane as shown in the figure. So if this is my x direction and the vertical direction is my y, so over x direction I have my width w and the height is h. So earlier in all the earlier scenarios, we were only considering heat transfer across x, so that is the temperature was uniform across y direction. Whereas in this case, you can see across y, that is at y equal to 0, we have this temperature T0, whereas at y equal to h, the temperature is T1. That is, temperature is varying along this y direction also. So over here it is y, and also if it can vary along x direction also. So in this scenario it is not particularly varying, but it can vary along x direction also. So in order to solve the second order partial differential equation, we introduce this dimensionless parameter, that is nothing but the temperature minus T0 upon T1 minus T0, where T0 is the temperature of the 3 sides, whereas T1 is the temperature of the sole side that is available. Then we define this eta, that is the ratio of x upon the height. Similarly, zeta is the ratio of y upon height. So this dimensionless parameter helps us to easily solve the second order partial differential equations. So yes, so basically this was our Laplacian equations. Now if I introduce this theta, that is t minus t1 upon t minus t0. So for example, over here, that is t minus t0 upon t1 minus t0. So I can replace it over here and get this equation in terms of theta. Now we will try to solve theta. That will be a function of x as well as y. So what we assume is that theta can be written in terms of 2 product or 2 different functions. So the first function is x, which is only dependent on x. Similarly, the other function will be y, which is only dependent on y. So this is dependent on y. So now in order to solve this second order partial differential equation, we will put this over here, and then we will use this variable separation form. And if we do that, that is put theta over here, theta equal to xy over here, so you will be getting such a kind of form. So this is minus 1 upon x d square upon dx square, then 1 upon y, second derivative of y. So this term is only dependent on x, whereas this term is only dependent on y. So let us assume this as some constant lambda square. So we can write it in terms of the second order ordinary differential equation given by these 2 equations 1 and 2. Now we know the solutions of this, general solutions of this equation, so we can get the x and y. So again, theta was a product of x and y, so we can write the overall theta as this. Now the only thing remaining to solve is this constant c1, and lambda will turn out to be n pi upon L. So depending on different boundary conditions, we can find the value of c1, c2, c3. So according to the boundary conditions as shown in this figure, that is at x equal to 0, the temperature is T0, and x equal to some W, the temperature is T0. So if we put those boundary conditions, then we can get the solution of this form. So this equation you need to remember. So for any given 2D systems, wherever this is my x direction, this is my y direction, if I have to find the temperature at any particular point, so let's say if it is 0, 1 and 1, if I had to find the temperature at say so where was I? So if I had to find the temperature at say let's say at some point 0.75 comma 0.75, so I need to replace this x as 0.75, similarly y as 0.75, then I need to expand this term till infinity, and then I can find the temperature. I hope that is clear. So this, and we need to do the summation over infinity, and then we can find this dimensionless temperature parameter, that is theta. But if you can find that, if you just consider first few terms, that let's say 4 or 5 terms, then also you can get sufficient level of accuracy. So you don't need to expand it till infinity. You can just consider for let's say 2, 3, 4 and equal to all those terms, depending on it might be asked in the question, and then you can decide how much do you want to expand this term. Okay, so now we will move on to the transient analysis, whereby the temperature will change with respect to time also. So let's consider this case of plunging a hot solid in a fluid. So in diagram, we have container whereby we have filled a fluid which has a temperature of T infinity, and then we drop a solid or a hot solid of temperature let's say initial temperature T0. So the moment we drop the temperature, this hot solid in this colder liquid, its temperature will start to decrease. So that is, the temperature will change with respect to time. So that is, temperature will be a function of time. So if we had to find the temperature at any given time instant, that is let's say time equal to 5 seconds, what will be the temperature or what will be the heat transfer rate? So in order to do that, we need to do this transient analysis. So the right hand, so we write the energy balance of this system, that is mcp delta T is equal to heat in minus, you can just write heat in minus heat out plus heat generation minus heat depletion. So if you will just write that heat balance equation, you can reach this equation, that is the rate of change of temperature within this solid block will be equal to the heat exchange, that is if the convection heat exchange is HA times T infinity, so both of them will be similar. So then we can solve this differential equation, that is rho Vc minus upon HAS is equal to dt by dt upon T minus T infinity. So you can just again write this as minus of 1 upon T minus T infinity dt is equal to HA upon rho Vc dt, and then you can integrate it. So since this is 1 upon x, it will become ln of x, and then you will put the limit from 0 to tau and T naught till T. So if you put those limit, you will be getting this equation. That is T minus T infinity upon T naught minus T infinity is equal to exponential of minus of HAT upon rho Vc, where this term is nothing but time constant, that is HA upon rho Vc. So yes, now once we have this temperature variation with respect to time, if we have to find the heat variation with respect to time, we can just straight away put HA theta and then integrate it across 0 to time in order to find the heat transfer rate, and it will be basically this equation: Q is equal to rho Vc theta I into 1 minus exponential of minus of T upon Ti. So in this transient analysis that we derived over here, we call this as lumped analysis. Because we assume that all the so basically we assume that all the parameters of this solid, that is the thermal conductivity or the temperature within the solid, will remain same throughout the solid block. But a more realistic scenario might not be the same. That is, we need to consider the validity of this lumped capacity analysis. So in order to validate that, or just to find different cases whereby we can use this lumped heat capacity analysis, we write the flux balance across this solid interface as well as the fluid. So that is, at the interface we will be there, if there is conduction within the solid and the convection outside the solid, then that two should be equal. Earlier we had not considered conduction within the solid, we were just considering this mCp delta T is equal to HA delta T. Now if we consider this flux balance across this, we can define this ratio, that is HL upon K, that we call it as Biot number. That is nothing but the ratio of the two resistance, that is the ratio of the conductive resistance upon the ratio of the convective resistance. That is, so this is the temperature difference across the solid and this is the temperature difference across the fluid. So this lumped heat capacity analysis is valid only for the cases where Biot number is less than 1. So if Biot number is less than 1, very less than 1, that means that the denominator will be higher and the numerator is lesser, that is T1 minus T2 is very less. So let's consider an ideal scenario, it is equal to 0. That implies T1 is equal to T2. That is what we studied, that is within the solid the temperature will be uniform, that is at any given x the temperature will be T1 will be equal to the surface temperature, that is T1 equal to T2 at any given x. So throughout the solid the temperature is same. So that is what we mean by Biot number is less than 1. This term, that is HAT upon rho Vc, we can also write it in terms of this Biot number and the Fourier number. So the exponential term will become nothing but exponential of minus of Biot number into Fourier number. So this Biot number is a very important dimensionless parameter that plays a fundamental role in conduction problem that involves surface convection effect. So yes, it can be interpreted as a measure of temperature drop in the solid relative to the temperature difference in the solid surface and the fluid. So that is what we had covered. So Biot numbers can also be interpreted as a ratio of thermal resistances. And in particular, if Biot number is very less than 1, the resistance to conduction within the solid is much less than the resistance to convection across the fluid boundary layer. Hence, the assumption of uniform temperature distribution within the solid is reasonable if the Biot number is reasonably small. that is Biot number should be less than 1. Now if the Biot number is not less than 1, that is if Biot number is equal to 1 or if Biot number is greater than 1, then we can see the special effects. That is, within the solid, the temperature at, let's say, x at r equal to 0 will be T naught, at r equal to 1 will be T1. So within the solid, the temperature will change. So for that, this lumped capacitance method won't give accurate results. So for that, we need to consider this more accurate scenario. So in the class we had covered this, the plane wall with convection, and we derived this solution whereby the constants were given by these equations. Similarly, if we consider an approximate solution whereby the Fourier number is greater than 0.2, then we can find a more simpler solutions, and that is useful in more practical scenarios also. That is nothing but C1 times exponential of minus of zeta square f naught cos of zeta into x star. So this parameters zeta and C1 you can see from the table, and corresponding to that you can find this theta at given x star. So yes, such kind of tables are available, whereby for depending on the Biot number we have this value zeta and C1. Then the other case we considered was this semi-infinite solid, whereby depending on the boundary conditions we can have different temperature distributions as well as the heat transfer rates. So the first one was the surface temperature, surface heat flux, and the last one was surface convections. So this basically says that if we have this semi-infinite solid, whereby let's say the length of y is fixed whereas the length of x keeps on varying, so that is the temperature along x will keep on varying and temperature of y will be limited to the length of y. So such kind of semi-infinite solid, we can write all this heat transfer rate and the temperature differential temperature distribution equations. So all these equations are valid for a 2D plane of infinite length, whereby if we had this different geometry, then we can use this table in order to find the exact solutions or approximate solutions. So yes, if you have any doubt in the theory discussed until now, you can just ask, or else we can move on to the next session, that is solving the questions related to the theory discussed. So we will start discussing the solutions in, let's say, 3 minutes at 7:45. Hello. So let's start by solving the first question of the day. So this question is related to the multiple fins case. So the question states that an isothermal silicon chip of width W is equal to 20 mm on a side is soldered to an aluminum heat sink of equivalent width. Okay. So we have this isothermal silicon chip of width W. So that is shown in this figure. So this is the chip of width W is equal to 20 mm and it has been soldered to an aluminum heat sink of an equivalent width. So this is an aluminum heat sink. It also has an equivalent width of 20 mm. Then the heat sink has a base thickness of 3 mm. That is, it says that this base thickness is 3 mm. And an array of rectangular fins, each of length LF equal to 15 mm. So it has this base which has the thickness of 3 mm, and then there is multiple fins of length LF. So this is the length of fins LF. Then airflow at T infinity equal to 20 degrees Celsius is maintained through channel formed by the fins and a cover plate. So over here we have this cover plate over here, and then we are passing the air of temperature 20 degrees Celsius through these channels, and the convection coefficient is given as 100 watt per meter square Kelvin. And then we have been given a minimum fin spacing of 1.8 mm, that is, this spacing is 1.8 mm. The solder joint has a thermal resistance of RTC is equal to 2 into 10 raised to minus 6. So we had soldered this chip to the aluminum heat sink using a solder, and the solder resistance is given by this 2 into 10 raised to minus 6 meter square per Kelvin and watt. So this will depend on the area, that is meter square. Then consider the array has 11 fins with the fin thickness T is equal to 0.182 mm, that is the thickness of fin is 0.182 mm, and we have this total N equal to 11, and the pitch is 1.982 mm. So the pitch is, I think, this difference between the two consecutive pins. Then if the maximum allowable chip temperature is Tc, that is, if the maximum Tmax of this chip is 85 degrees Celsius, then we have to find the overall surface efficiency eta naught and the chip power Qc. So this is the case of multiple fins, whereby we have been asked to find the overall surface efficiency and the chip power Qc. So you can try solving these questions. I will just share the question and the formulas necessary for it, and then you can try solving it. So this was the description of the questions, and these were the questions that we have to solve. And the necessary formulas I discussed over here. Were this. So the one required will be the formula for area and naught, and Q you can straight away find using this resistance concept. So you can try solving this question, guys. So right now it is 7:50. We will discuss the solution at 8 p.m. So you have to first calculate the area through which the heat transfer is occurring. Then you have to find this the efficiency of individual fin NF, and then straight away put all those values in this equation. That will give you the efficiency. And then in order to find this chip power, you can just write Q is equal to delta T upon R, and then you can try finding the chip power. So the R over here will be a combination of R convection that will occur through the air plus R conduction that will occur within the solids, and then there will be also this chip resistance over here, that's a shoulder resistance. So you can just put those, well, calculate the individual resistances, sum them and put over here, and you will get the QC, that is chip power. So try solving it on your own, and then we can discuss the solution. So sorry for this. So this will be a combination of three, but it won't be convection conduction. It will be the resistance due to this overall fin. So not this conduction, resistance due to the overall fin. So formula for that was H1 upon efficiency of the fin upon 1 into 80. And then as discussed, then we will be having the resistance due to the shoulder, that is LTTC. And then the resistance due to the conduction within this this block. So yes, that is our conduction. So yes, this is basically convection resistance, but you have to consider the overall fins. So let's try solving this question. Okay, so let me just again copy this thing. So the first thing we were asked was we had to find this eta naught and QC. So the formula for this overall surface efficiency eta naught is given as 1 minus n AF on AT into 1 minus eta F. Now EF is the overall heat transfer area through which the heat transfer would occur. No, that is AT. So AT is the overall area through which the heat transfer would occur, and AF is the overall area of the fins. So that is, we can write this AT as nothing but N into AF times plus AB So we need to find this AF 80. So N is the number of fin, that is 11. So one thing that we have to find is this 80. The other thing that we have to find is the fin efficiency, that is the individual fin efficiency, that is eta F. And for this kind of this rectangular fin, we already studied in earlier class that the fin efficiency is defined as hyperbolic tan ml length of fin upon ml f, where m is under root of h p k upon a. So yes, we need to find these two parameters and then put it in these equations. So the first thing, let's just calculate this AB. So this should be AB, area of base, and the AF is the area of fin. So AF is equal to area of fin, so area of individual fin. So the width we were given as this W over here, you can see. So the area through which the conduction, the area through which this convection will occur in individual fin, we can write it as twice of W into this length of the fin is L, WLF, and on the other side it will also be WLF, that is twice of WLF. So the width is given as 20 mm and the length of the fin is given as 15 mm. So this will come around 6 into 10 raised to minus 4 meters square, that is AF. The other thing we need to find is the area of the base, that is the part whereby we don't have the fin. So that will be nothing but the overall base area minus the area which has been occupied by the fin. So the overall base area for this square silicon chip will be, overall area is W square, and we have to subtract the area of this in area of the area occupied by the fin. So there are n fins, and each individual fin will occupy this area of width W and thickness T. Okay, so that is n times W into thickness T. So again you can put this as 20 into 20 into 10 raised to minus 6 minus of 11 into width is 20 mm, thickness of the fin is thickness is 0.182 mm. So yes, you can try solving this and you will be getting it around 3.6 into 10 raised to minus 4 as AB. So this AB and AF you can put over here, and if you put, you will get the value of AT as 6.96 into 10 raised to minus 3 meter square. Now you need to find this efficiency of individual fin. So for that you need to find this M. So M we defined as under root of HP by KA. So the perimeter for this fin will be thickness times width, that is width plus thickness, correct? Width plus thickness into 2, twice times width plus thickness. And okay, and the cross-sectional area to which conduction will occur is W into T. So this thickness is very less as compared to W, so we can just neglect this. So for example, the width is 20 mm and the thickness is 0.182 mm, so we can just consider this as 0, cancel this term, and we will be getting 2h upon kt as our m. Again you can replace the value as h is given as 100 watt per meter square, thermal conductivity K is given as 180, and thickness is I think given as 0.182. Yes, thickness is 0.182. So if you put the values, you will be getting the value of M as 78. So put the value of M in this equation and you will be getting the value of eta F as 0.704. Now put the value of AF, AT in this equation of this eta naught, that is eta naught is 1 minus of 11 times area of fins we calculated as 6 into 10 raised to minus 4 upon total area is 6.96 into 10 raised to minus 3 into 1 minus individual fin efficiency, that is 0.704. So try simplifying this and you will be getting the overall surface efficiency as 0.719. So as the individual fin was 0.704 and the overall fin efficiency is 0.719. Then we had to find this Q chip power, so that I already discussed. It is nothing but delta T upon R, where R is nothing but the combination of three terms R1, R2, R3. So R1 is the resistance due to this overall fin, so that we already discussed as 1 upon eta naught H into AT. Similarly, then there will be this resistance due to this soldering. So this soldering resistance is straight away given as 2 into 10 raised to minus 6, and it is in terms of meter square. So we need to divide it by the total area so that it is in terms of K, temperature difference upon the heat transfer, that is K upon W. So the units of resistance should always be the temperature upon the energy, that is heat transfer rate. So let's divide this R double dash by area, that is W square, and then at last we will be having this convection occurring at the base, that is thickness, that is LB upon K times, and the cross sectional area will be W square. So the overall temperature difference, so at the top I think it over here we were giving the temperature as 85 degrees Celsius and the air was at 20 degrees Celsius given over here. So yes, if you put those values, 85 minus 20 upon R1 plus R2 plus R3, so this will come around 2, this will come around 0.005 and the third resistance will be 0.042. Just sum them, and if you put over here you will be getting QC as 31.8 watts. So that is the chip power is 31.88 watt. So that was the solution to question number 1. That is the fin overall surface efficiency found out as 0.719 and the value of chip power QC was 31.8 watt. So this is the solution in brief. Now this is the question related to this 2D plane. So we have been given this 2-dimensional rectangular plate and we have been asked to find the temperature at the midpoint, that is at x equal to 1 over here and y equal to 0.5. That is, we have to find the temperature at this point. So we can use straight away use the formula that we derived for this 2D systems. So you can try solving this question. I will just share the formula and then we can discuss the solution. So this is the question, and for 2D plane the formula that was derived in class was this one. So using this formula you can try finding the temperature at the midpoint, that is at x equal to 1 and y equal to 0.5. And we have been given that we have to consider the first 5 non-zero terms of this infinite series. So try solving this and we will solve this question in 2-3 minutes. So let's try solving this. So the solution to this question is simply very straightforward. We just have to use the equation that has been provided in order to find the temperature at the midpoint. So one thing to keep in mind is this temperature, this dimensionless parameter, that is theta, that we defined as t minus t1 upon T2 minus T1, where T1 is 50 degrees Celsius, whereas T2 is 150 degrees Celsius. And then we have to put the value of n is equal to 0, 1, 2, 3, 4, 5, 6, similarly. So what if you just keep on putting the values of n, so you will find that if n is even number, that is n is equal to 2t, that is 0, 2, 4, 6, 8, this value sine hyperbolic h, or this the value of sine n will becomes twice of let's say twice of some number into pi x upon L. So this thing is constant, so this term will become 0. That is, for all the even values of n, this all the parameters will become 0. So we just have to consider the odd values of n, that is for n is equal to 2t plus 1. That is, we have to consider n is equal to, if we put equal to 0, that is 1, 3, 5, 7, 9. So in the question we had to ask, we were asked to consider only the first 5 non-zero terms. So we will put the value of n is equal to 1, 3, 5, 7 and 9 in these equations. So if you put the value of n equal to 1, so what it will become, that is theta will become, so 2 upon pi will become remain the same, minus 1 raised to n equal to 1, so minus 1 square will be 1, 1 plus 1 is 2 upon 1, that is 2 into sine of pi x by L sine h of pi y by L upon sine of h into pi w by L, plus all those terms corresponding to n equal to 3, 5, 7, 9. So then we need to put the value. So the value of x will be 1. So that is x upon L. This value we can straight away put as x is 1 and the length is 2. So x upon L is 1 by 2. Then y by L will also be y is I think 0.5 and L is this maximum length 2, that you need to remember, not this length, it is just 2. So L is 2, so it will become 1 by 4. So just put the value of x by L, y by L in all those 5 equations, and then you will be getting this theta at 1, 0.5 as 2 by pi into all those 5 terms. So if you just try solving this, you will be getting the value of this theta as 0.445. So that is nothing but t minus t1 upon t2 minus t1, and we have to find this t. So this t will become 0.445 into t2 and t1 were, t1 is 50 and the other thing is 150. So that is 150 minus 50 plus 50. So this will become 44.5 plus 50. So this overall term will become 94.5. So this is our temperature, 94.5. So yes, we straight away use this equation in this question to solve the question. Now the third question is related to the lumped heat capacity analysis. So these are very straightforward questions. So I will just share the solutions straight away with you after discussing. So yes, so this question says that a flaked cereal of thickness 2L equal to 1.2 mm is given as shown in the figure. So the thickness of this flake is 2L, that is 1.2 mm. The density, specific heat and thermal conductivity are given. The product is to be baked by increasing its temperature from T0 is equal to 20 degrees Celsius to Tf is equal to 220 degrees Celsius. The convection oven through which the product is carried on a conveyor. If the length of the oven, that is L0, is 3 meter long and the convection heat transfer coefficient at the product surface interface and the oven temperature are this. So H is given as 55 and the T ambient is given as 300 degrees Celsius respectively. Then we have to find the conveyor velocity, and then we have been given this other case where if we reduce the thickness to 1 mm, what should be the required velocity. So in order to calculate the velocity for this fixed length, we need to find the time. So this question basically we have to use this lump capacitance analysis in order to find the time taken by the flake to reach the temperature of 220 degrees Celsius, and then by using this time we can calculate the required velocity. So let's try solving this question. So from the lumped heat capacity analysis, you must have remembered this formula, that is HAT upon rho Vc is equal to ln of T0 minus T infinity upon T minus T infinity. But this equation is only valid if Biot number is less than 1. Is very less than 1. So the Biot number we calculate as HL upon K. So the heat transfer coefficient over here is given as 55. The characteristic length for this cereal will be volume upon area. So the area will become so if the width is W and the length is L, let me just consider this as the flake. If this is my flake, the width is W, length is L. So it will be, so let's just see in the question. So in the question we have been given the thickness as 1.2 mm, that is thickness 2L is 1.2 mm. So for a given flake, this thickness is 1.2 mm. So if we just find the characteristic length for this surface whereby the convection will occur through both of these surfaces. So since the convection is occurring through both of the surfaces, the characteristic length will become L upon 2. So if you just put those values, you will be getting the value as 1.2 by 2 upon value of K as 0.34. So this will come around 0.098. So this is very less than 1. So we can see that the LC analysis, that is lumped capacitance analysis, is valid. So then we can straight away use this formula in order to find the time. So this A by V, you can replace it at T, and we will be getting the value of time as rho L C upon H into ln of T naught is the initial temperature of the flake, that is 20 degrees Celsius, minus the ambient temperature is 300 degrees Celsius, upon we have to bring the temperature to 220 degrees Celsius, minus 300 degrees Celsius. So you can put all those values and you can get the value of time, that is the time taken by the flake to reach a temperature of 220 degrees Celsius will be approximately 23 seconds. So that is the velocity will become the length, that is L naught upon time. So it is 3 upon 23. So it will become 0.13 meter per second. So similarly, in the second case, we were given that if the thickness was now instead of 1.2 mm, it becomes 1 mm. Then what is the velocity? So you can try solving using the same principle and you will be getting the velocity as 0.16 meter per second. So you can try solving it and you will be getting this same velocity. So that was the third question of the day. So from this formula over here you can also see that so we know that velocity is distance upon time, so velocity is inversely proportional to time, and again from this equation we know that the time is directly proportional to the V by A, that is time is proportional to the characteristic length, that is V1 upon V2 is equal to T2 upon T1 is equal to L2 upon L1. That is, we can straight away write this equation, V1 upon V2 is equal to L2 upon L1. So L2 is nothing but the thickness, and then you can put the values over here, and alternately in this by shortcut method you can also find the velocity as 0.16 meter per second. So this is question number 4, which is again a lumped capacity analysis. So try solving this and we can discuss the solution. So I will read out the question. So annealing is a process by which steel is reheated and then cooled to make it less brittle. Consider the reheat stage for 100 mm thick steel plate, and we have been given these parameters, which is initially at uniform temperature Ti is equal to 200 degrees Celsius and is to be heated to a minimum temperature of 550 degrees Celsius. Heating is effected in a gas fired furnace where products of combustion at T infinity equal to 800 degrees Celsius maintain a convection coefficient of H equal to 250 watt per meter square Kelvin on both surfaces of the plate. How long should the plate be left in the furnace? And then we have been given these parameters. So if you try solving this, you will see that the Biot number for this case will be very greater than 1, and that is why we have been given these parameters. So in this scenario, we can't use this lumped capacitance analysis, and we have to use this full system whereby the special effects can be observed. So for that, I will just share the solutions, and then you can try I will just share the formula, and then you can try solving it on your own. So far we discussed these formulas. So yes, we will use this approximate solution. So we have to use this formula over here in order to find the length of how long should, in order to find the temperature, in order to find the time taken by time taken, that is T. So you need to remember this Fourier term will be having this time term, that is Fourier number is nothing but alpha t times L square. We have been given C1, we have been given zeta. So this straight away at x equal to 0, you can consider that you can consider this as 1. That is, you will be having theta star is T naught minus T infinity upon temperature at any given time upon T infinity is equal to C1 times exponential of minus of zeta square into F Fourier number. So you have to use this formula in order to solve the question. So we take this x star as 0 because in the question we have been given that the minimum temperature is 550 degrees Celsius. So the minimum temperature will occur when it is at the center of the block. So basically this steel block, the temperature will be minimum at the center of the steel block. That is why we are taking x star as 0. That is cos of 0 will become 1. So this is the straightforward application. So the first thing that I already discussed, that for this system you need, if you had calculated the Biot number, it would have come around 0.26. That is very greater than 1. No, that is very greater than 0.1. So in the earlier question also, over here also, so the Biot number should be less than 0.1, then only the lumped heat capacity analysis is applicable. But in our question, the Biot number will come around 0.26. That implies we need to use this full analysis. Then you need to straight away put those values over here. So the T naught, that is the initial temperature, is which is heated uniformly at a temperature of 200 degree Celsius. So this T naught is not the initial temperature but the temperature to which we want to heat this system. So if you just put the values, it will be 550 minus the ambient temperature is 800 upon Ti is the initial temperature, that is 200 minus 800 is equal to C1 is 1.0 396 into exponential of minus of 0.488 square into alpha t upon L square. So time is we have to find. The L will be the thickness. L should be the characteristic length in this case. So similarly, you need to find the value of this alpha. That is, alpha is nothing but k upon rho c. So if you calculate the value of alpha, it will come around 1.1 into 10 raised to minus 5. Then you can put all those values and you will find that the time taken by the system to reach the temperature of this 550 degrees Celsius will be 861 seconds. So you just need to put those values and you can get the answer. This is the solution. I'm sharing the solution, so it will be around 8.861 seconds. Then let's take this question of this semi-infinite geometry. So both the last two questions are similar. The lumped heat capacity analysis question also we discussed. So let's just take this one example related to this semi-infinite geometry. So here I have also given you the formula, but I will just first read the question. So we have been given that asphalt pavement of these parameters may achieve temperatures as high as 50 degrees Celsius on a hot summer day. Assume that such a temperature exists throughout the pavement. When suddenly a rainstorm reduces the surface temperature to 20 degrees Celsius, calculate the total amount of energy that will be transferred from the asphalt over a 30-minute period in which the surface is maintained at 20 degrees Celsius. So we have been given an asphalt pavement. So let's just consider this as an asphalt pavement of the width W, and then we have been, the length is infinite. So this is the infinite. So we have been given that in summers it can reach the temperature as high as 50 degrees Celsius. Now if a rainstorm occurs, that is, let's assume if rain falls, then the surface temperature can reduce to 20 degrees Celsius. So in that scenario, we need to find the total amount of energy that will be transferred from the asphalt over a 30-minute time period, in which the surface is maintained at 20 degrees Celsius. So the heat flux for this semi-infinite solid is given by this equation, and we have to find the overall energy transferred for this 30-minute period. So what you will do is, you will straight away integrate this in order to find this equation from 0 to 30 minutes, and q double dash of t dt. So you can put the values over here as k into ts minus ti upon under root of pi alpha t upon dt. So t is the only variable, so t raised to minus 1/2 integration would become t raised to half. So all this constant will remain same, ts minus ti upon under root of pi alpha, and the integration of 1 upon root t will be root t. And over here you have to put the limits 30 to 0. For 0 it will be 0, and for 30 you can find this as the value of k is 0.062 into t s is 50, and one is 50 and one is 30. So 50 minus 20 upon under root of pi into alpha is k upon rho c, so that you can find it as 3.18 into 10 raised to minus 8. So if you try, and then under root of 30. So if you try solving this, you will be getting the overall energy transferred as 4.99 into 10 raised to 5 joule per meter square. So this is our required answer. So if you have any doubt in these 5 questions discussed today, you can ask me. I will be here for around 10-20 minutes. You can ask any doubts related to any of the topics. So if you have any doubt, you can ask me. I am still here. So if you don't have any questions, we can end today's class. So thank you for joining.